Okay, in the last couple of videos, we were talking about the fundamental counting principle, and we tried to apply it to just some really basic examples. And then in the video immediately preceding this one, we applied the fundamental counting principle to a permutation type problem. That is, where we had just 4 distinct letters, and we asked ourselves, how many ways can they be arranged where the order matters? For example, if we had this, that's a different arrangement than this. The letters are the same, of course, but the order of the letters is different. And we demonstrated in the previous video that the answer to that is 4 factorial. And we obtain that by using the fundamental counting principle. Or if we had just n number of distinct objects, and we wanted to know what's the number of ways that we could arrange them where the order matters, that would be n factorial. Or what you'll hear us say sometimes in the future videos now is, if we have, for example, 4 distinct letters, what's the total number of ways that we could permute those letters? That's, again, 4 factorial. So that we say we're going to permute these different letters. What we mean is we're going to have different arrangements for them, and the order of the arrangements matters. So that's just to catch up where we were before. What we want to do is consider another type of basic permutation problem, but one that is a little bit more complicated. And it has 4 parts to it. It starts off like this. Let's say that we had 6 men and 3 women. And let's say that we have a row of 6 empty chairs to seat them. The first question is, if there's no restrictions, that is, there's no particular man or woman that has to be seated together, if there's no restrictions, how many different ways could we seat these people in the 6 different chairs? And of course, the answer to that is just 6 factorial. And that's just written like this, which equals 720. So there's 720 different ways that these people can be seated. The 6 different individuals can be seated on the 6 different chairs to occupy them. Okay, now let's put some restrictions on the problem. Let's say that we want to have them seated so that you have alternating pairs, man-woman or woman-man. It doesn't have to be any particular couple, though. We want to have an alternating man-woman pattern. How many different ways could we do it that way? Now here's where the problem gets to be more interesting. First of all, we have to realize there's 2 different ways that that pattern can be achieved. The first chair could be occupied by a male, and of course you have to have a woman immediately after him, so the pattern would look like this. Or the first chair could be occupied by a woman, in which case the pattern would look like this. So either way, it gives us an alternating man-woman pattern. What's the total number of ways that we can achieve then an alternating man-woman pattern? Well, let's consider this first, where the first chair is going to be occupied by a male. How many different ways can we produce this type of pattern? And we can answer that question again by using the fundamental counting principle. And we consider it like this. Well, let's say we have 6 empty chairs, and the pattern is the first one has to be occupied by a male. So let's say that the males have occupied their seats. So task T1 is, well, how many different ways can the 3 different women occupy the remaining 3 different seats? And of course, the answer to that is just 3 factorial. And the pattern to that would look something like this. See, all the males have occupied their particular seats. That doesn't change. What changes now is that we're permuting the ways that the woman could occupy the 3 empty seats. We said the answer to that was 3 factorial, which of course is just 6. 3 times 2 times 1. And here would be the 6 different possible arrangements. Okay. Well, let's consider this. Let's say that we want to have the same general pattern, that is where the male occupies the first seat, but let's say that the woman occupied their seats first, and then the men are going to occupy their seats. So now we have 3 different men and 3 different seats for them to occupy. How many ways could that be done? Of course, the answer to that is just 3 factorial. And this is our second task. And that gives us the man-woman pattern, where the man occupies the first seat. So what's the total number of ways that we can get this pattern? And here's where we use the fundamental counting principle. Because the total number of ways of accomplishing T1 is 3 factorial. The total number of ways of accomplishing T2 is 3 factorial. Together, it would be 3 factorial times 3 factorial. Of course, that's just 6 times 6 equals 36. Now, before we go on, for this one right here, where the women occupied their seats first, and then we permuted the men, what that would look like is this. Here the women are in their particular seats. That doesn't change. What changes is the 3 remaining males to occupy the 3 remaining empty seats. We can permute that 3 prime or 6 numbers, different, not 3 prime, but 3 factorial number of ways, or that's 6 different ways, and here they are right here. So this is for task T2. Okay. Well, task T2 and task T1 together gives us this arrangement. So the number of ways that could be done then is the number of ways that we can perform task T1 times the number of ways that we can perform task T2, or that's 6 times 6 is 36. So the number of ways that we can produce that pattern is 36. Now, if a woman occupies the first seat to give us this, we're clearly applying the same logic, and in fact the same numbers. The number of ways that this could be accomplished is 36. So that means then the total number of ways in which we could have a seating pattern where men and women alternate each other would be 36 plus 36, or that would give us 72 ways total. Okay, well, let's say that we want to consider this problem. Here we had just man-woman or woman-man without regard to whether any particular couple had to be seated next to each other. But let's say that out of the 3 men and 3 women, let's say that one couple always had to be seated next to each other. How many different ways could that be done? So we have our men, 3 men, and 3 women. And one of these couples can never be separated. So now how many different ways can we have that seating arrangement? First we have to realize, okay, if this couple is always going to remain together, that could be done in 2 different ways mainly. We could have the male sitting to the left of the woman, or we could have the man sitting to the right of the woman. Well, let's consider this possibility first. How many different ways then can we have the seating arrangement so that the man and the woman are always together, and the man could be on the left or the right, we'll just consider this arbitrarily as being the first possibility. So here, the key, though, is that we're looking at this, realizing these people can never be separated. So we treat them as one object. That means now, out of the group, there's 4 other separate objects. Here, 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 here. So we have a total of 5 separate objects that we can permute. The number of ways we can do that, of course, is 5 factorial. And this is 20, as it gets 120 ways. There's 120 ways, then, that we could have this occur. Well, applying the same logic, there's going to be 120 ways in which this could occur. Because again, we're treating the man and the woman as one object. There's 4 other people, there are 4 other objects. Again, a total of 5 objects to permute to give us 120 ways. So, the total number of ways in which people can be seated so that this couple is never separated is 240 ways. So that's the total number of seating arrangements whereby this couple here always remain together. Now, if you wanted to ask a more restrictive question, how many different ways could this couple be seated so that the man is always on the right? Of course, that would be 120 ways. But 240 ways total. Okay. Well, now for the last part of the problem, let's ask this question. How many different ways can these people be seated so that this particular couple never sits next to each other? Well, to answer that question, we go back to the beginning part of the problem. We realize that there were 6 factorial, or 720 total number of seating arrangements. That's the total number. The number of seating arrangements in which the couple is always together is this. So, of course, the number of seating arrangements where they're always going to be separated would be 720 minus 240, or that would be 480 ways, or 400 different seating arrangements, say, in which that couple never sits together. But okay, that's it for this problem. Hopefully this was a little bit more, made you think a little bit more than the previous ones that we had. And come back and join us for some more videos. We're going to try and consider some more complicated permutation problems and also how to handle combination problems. We're going to do that in the next couple of videos coming up here. So come back and join us for those videos and we'll continue our discussion.